So good morning to all of you. Today there is another numerical, and this numerical is basically based upon the design of transformer. And here in this case of design of transformer, you have to design the two main things. The number one, you have to calculate its main dimension, and the main dimension is the same thing, that is you have to calculate its magnetic frame. And the second part, that now you have to calculate it's the winding detail or the winding design. Now what will be happen in case of a winding design, what we have to calculate actually in the winding design, we will discuss in this numerical. uh, if I talk about the main dimension, as we all know that in the main dimension we have number of steps, like we have to calculate its ET, then we have to calculate its phi m, then you have to calculate its net iron area, AI, then gross core area, that is AGI, then you have to calculate its AW, that is window area. After that we have height of the window, after that we have the width of the window, and after that we have the area of the yoke. So when I combine all these factors, you are getting a main dimension, or that is called as the magnetic frame design. But if I talk about the winding design here we have to calculate number one, number of turns on the low voltage side, number of turns on the high voltage side. Another thing, we have to calculate the current on the low voltage side, current on the high voltage side. Number three, we have to calculate the area of the low voltage side and area of the high voltage side. So basically here we have to calculate the three main things in winding design. The number one will be turns on the low voltage or the high voltage, or you can say that turn on the primary winding as well as the secondary winding. Number two, uh, what is the you can say that the area of the winding that we can use in the that we can use in primary side or a secondary side. And number three, what is the value of the current on a low voltage side as well as the high voltage side. Reason being, value of the voltage will be given in the numerical. When a client has to be given a numerical, or when the client has to be given a transformer has to be designed, then the voltage will be given to us, but the current is not given. So firstly we have to calculate the current. Clear? So what we have to do, the design of this transformer, and here you can see this is the basically the data that are provided by the client. Calculate the main dimensions and the winding design of a given transformer. We have Q is equals to 5 kVA, voltage is equals to 11,000 by 400 volt, frequency is equals to 50 hertz. Then you have a single phase core type distribution transformer. Some more data it will be given to you, that is maximum flux density is equals to 1 vapor per meter square, current density is equals to 1.4 amperes per mm square, window space factor is equal to 0.2, the height of the window is equals to 3 times the width of the window, that means HW is equal to 3 times WW. Now based upon this design you have to calculate the main dimensions, and after that you have to calculate its winding design. It is clear? Yeah, it is clear to all of you that what we have to design. We have designed basically here,
Yes, sir.
we have to design the two main things. The number one, we have to calculate its main dimension, जैसा हम करते आ रहे हैं. And second part में, now today we were discussed about its winding design, how the winding of this transformer can be calculated. Clear? So can you people start? You do one thing, you will start and calculate its main dimension, and we will discuss with the main dimension with you people, and after that I will tell you that what is the winding design for this transformer and how the winding design of this transformer can be calculated. Clear? So I think you people will start and try to solve this numerical. So very first step, what is the very first step? Very first step is called as ET, that is EMF per turn. So ET is equals to K under root Q, isn't it? So the formula will be ET is equals to K under root Q, and we all know that the value of K we have to be assumed. Now, the transformer that we have given is a single phase and moreover core type distribution transformer. So when I go to the value, the K is equals to 0.75 to 0.85. So when you solve this value, your ET will become as 1.6257. So check it, either this value will be got or not.
Yes, sir, it is the same.
Is the same value? Okay, fine. So Vinayak, you got this value, that is ET is equal to 1.6257. Yeah,
Yes,
Vinayak.
sir.
Okay, fine. So
Yes, sir. Yes, sir.
everybody get the value except other than Vinayak, Manhar, Neha, Himanshi. Can you get this value?
Yes, sir. Yes, sir.
Okay, fine. So this is the step number one, and if you proceed to the step number two, you know that when you calculate the step number two, in case of step number two, we have to calculate the value of flux. So you can use the formula that is Et is equals to 4.44 into F into phi m. So when you substitute all these values, your Et will become as 1.6257 is equals to 4.44 into 50 into phi m, and from this value you can get a value that is phi m is equals to 7.322 into 10 raised to power minus 3 Weber. So in this particular numerical, your Et, that is EMF per turn, is equals to 1.6257 and your flux is equals to 7.322 into 10 raised to power minus 3 Weber. Are you got this value? Are you got this value?
Sir, it is the same.
It's the same value. Shall I proceed now?
Yes, sir.
Shall I proceed now?
Yes, sir.
Uh,
Yes,
Yes,
sir.
sir.
Okay, fine. Now, after the step number two, you have to calculate its net iron area, and the formula for that thing you have AI is equals to phi m upon bm, isn't it? Now you can see your value of phi m is equals to 7.322 into 10 raised to power minus 3, and in this numerical, the value of bm that you should see from the top, the value of bm is equals to 1 Weber per meter square. So when you get a value here, the AI will be equals to, that is 7.32 into 10 raised to power minus 3. So the AI, that is the net iron area, is equal to 7.322 into 10 raised to power minus 3. Got it? Yeah, Vinayak, what is the problem? Vinayak, Vinayak, what is the problem? Now it is audible or not?
Yes, sir. Yes, sir. Now it is audible.
Okay.
Sir, but
So,
you said that value of BM lies between 1.3 to 1.5.
yeah,
Why
exactly.
in this case it is taken 1?
I will tell you that the value of BM will lies between 1.3 to 1.5. The question is that thing, if the value of BM is not given in the numerical, then in that case you can take a value of 1.3 to 1.5 Weber per meter square. But the question is that thing, whenever you get a design, in a design, which value is given to you, you have to use that value. So you see in that particular numerical, you can see the maximum flux density BM is 1 Weber per meter square is given to you. That is why I can use this value. If this value of BM is not given to me, then I can't use this value. Is it clear now? So the question is if the value of BM is not given in the numerical, then you can use the value BM is equals to 1.3 to 1.5 Weber per meter square. But if the value of the BM is not given in the numerical, then you can use the value BM, that is 1.3 to 1.5. But if the numerical value is given in the numerical, then you can use that particular value. For example, in case of a current density, I can give you the value that the current density will be equals to 2.4 amperes per mm square. But now in this case, in this numerical, the current density is given as 1.4 amperes per mm square. So we can use that particular value here. Okay, fine.
Yes, sir.
So if you see your step number 3, your net iron area will be equal to 7.322 into 10 to the power minus 3. Clear, bache?
Yes, sir.
Okay. Now
Yes, sir.
after that, you all know next value will be your AGI, and this AGI is called as the gross core value. And you know that AGI is equals to AI upon stacking factor. Now, what is the value of stacking factor? That is 0.9. We all know. So we have AI, that is 7.322 into 10 to the power minus 3 upon stacking factor. The stacking factor will be equals to 0.9. So when I divide this value, you can get a value that is AGI is equals to 0.008136 meter square. Clear, bache? So we can get a value of AGI,
Yes,
that is
sir.
gross core area, is equal to 0.008136 meter square. So आप लोगों की ये values निकल रही है ना, जब आप अपनी places पे निकाल रहे हैं ये values.
Yes, sir.
yes, sir. Same.
Okay, fine. See, अभी तक मैंने अपने ट्रांसफॉर्मर में वाइंडिंग डिजाइन शुरू नहीं किया because in our numerical we have to calculate the two main things. The number one will be the main dimensions and another will be the winding details. So here I can calculate only the main dimension, and once the main dimension will be over, then I will proceed towards the winding design. Clear, bache? Okay, after that I can skip here the value of 80 or the value of R, because the value of 80 and this R is not important yet. We have to calculate its value of 80 as well as R in the main dimension, but if we ignore that value, it will be okay. So quickly I will go to the value of AW, and we know that the value of AW, that is the window area, can be calculated by the output equation. And since it is a single phase transformer, so you know that in case of a single phase transformer, Q is equals to 2.22 into F into phi m into AW into KW into current density into 10 to the power minus 3. So here, what is the value of Q? That is 5. 2.22 is constant. F is frequency 50. Phi m we have 7.322 into 10 to the power minus 3. AW we have to calculate. KW it is given 0.2. Current density is also given, that is 1.4 amperes per mm square. I can change this value in amperes per meter square, that is 1.4 into 10 raised to power 6 into 10 raised to power minus 3. So when I solve this value, you can get a value AW is equals to 0.021968. So are you people getting this value? You take your time and get the value, and once this AW will be becomes, then we will proceed further.
Sir,
Yeah.
sir, please explain this. Why it is 10 raised to power 6?
The reason being, you can see, Vinayak, you can see here the value of current density, that is 1.4 ampere per mm square. Clear? That means
Sir, yes, sir.
current density is current density. What do you mean by this current density? Current density means current per unit area. Density is per unit area.
Yes, sir.
So current density
Yes,
means
sir.
current per unit area. So current is 1.4 ampere, and per unit area, that means mm square. We can take this area in mm square. Clear? But now when I calculate this value in
Yes,
here,
sir.
you can see if this AW is in meter square. The value of AW is in meter, but here current density is mm. So we have to convert this mm into meter now. I have to convert this mm into meter. So that is why when I convert this AW,
Yes,
sorry,
sir.
current density is equal to ampere per mm square into meter square, then we have to multiply it with 10 raised to power 6. That is why I can change this value. Okay. Yeah, Vinayak, okay?
Yes, sir.
Fine. So, are you getting this value? AW is equal to 0.021968.
Yes, sir.
Okay, fine. Fine. So, Neha and Imanshi get a value. Manhar, are you getting this value?
Yes, sir.
Okay, again. So, you can find this value, that is AW is equal to 0.021968. Clear? So, shall I continue?
Yes, sir.
How much the difference will be you got?
Sir, 0.02197.
No issue at all. It will be 0.021698. Now, I will tell you that in a design, there is a slightly changes in the answers. Okay, so you can get a value, that is AW is equal to 0.021968. Shall I continue
Yes,
next?
sir.
Shall I continue next?
Yes, sir. Yes, sir. Yes,
Okay.
sir. Yes, sir.
Okay, now we have to separate this AW in the terms of HW and WW, and also we know that this AW will be equals to the product of HW into WW, and in this numerical we are given that is HW is equals to 3 times the WW. Now I can use this value, and after that we can get a value that WW is equal to 0.08557 and HW is equal to 0.25627. So you take your time and get this value. Either you got these values or not. If you got these values, it is okay. If you not got these values, kindly go through and separate this AW in the terms of HW and WW. That means when you get an area of the window, you have to segregate, or you have to separate this area of the window in two terms. That is, what is the height of the window and what is the width of the window. So in this case, we know that the height of the window upon the width of the window lies between 2 to 3, but here the height of the window is given as 3 times the width of the window. So based upon that thing, you can get a value, that is what is the value of WW and SW. So anybody got this value after separation?
Got it.
Got it? Okay, good, very good. Vinayak, you got it, the value that is WW is equal to 0.08577 and HW is equal to 0.25627. Is anybody got this value?
Yes, sir.
Sir, there is slight more difference.
Yeah, tell me.
It is 0.2567.
No issue at all, na? No issue at all. You can see your
0.25.
yeah, you can see in my case the value will be 0.25 and your case is be 0.257. Now my case 0.256. So it is almost equal to it is almost equal to the same thing. No issue at all.
Same, sir.
Okay, very good, Sarthak. Very good, Sarthak.
Yes, sir.
Okay, very good, Neha. Himanshi. Shall I continue next?
Yes, sir.
Shall I continue next?
Yes, sir.
Okay, is it the numerical will be clear to all of you?
Yes,
Na?
sir.
Yes, sir.
Is the numerical will be clear to all of you? Can understand this
Yes,
thing? Na?
sir. Yes, sir.
Yes,
Yes,
sir.
sir.
Fine, fine, fine. So shall I proceed now?
Yes, sir.
Yes, sir.
Yes.
Okay, now next step we have to calculate its you can say that AY, that is called as the yoke area, and this yoke area will be equals to 1.1 AGI. So here what is AY? That is 1.1 into AGI. So you can got a value that is AY is equal to 0.00895 meters square. Clear bache? So up till that stage we have to calculate its main dimension, और यहाँ तक हमने अपने ट्रांसफॉर्मर की जो मेन डायमेंशन थी वो निकाल दी. इन मेन डायमेंशन वी हैव ET, you have phi m, you have AI, you have AGI, you have AW, you have HW, you have WW, and you have AY, isn't it? So everybody got this value that is AY is equal to 0.895 because up till that stage you are covered. यहाँ तक जो आपने निकाला है ये हमने पीछे सारा किया हुआ है. Now इसके बाद today we will start with the second design that is called as a winding design. How the winding in case of a transformer we have to calculate and how the winding of the winding design can be made in case of a transformer. Shall I continue or I can wait?
Sir, please continue.
Okay, fine. So now my humble submission to all of you, please now keep your books and your pens on one side. First of all, you can see कि हम लोग डिजाइन करते कैसे हैं. After that, I will provide this study material in your WhatsApp group and also I will provide the video of this thing. You can watch the video again and again so that you can get an idea. And after that, you can again the study material will be provided to you. So you can get an idea that how the winding design to be calculated. Clear? So I can again tell you in case of a winding design of a transformer, we have to calculate the three main things. Number one, turns on the low voltage side, turns on the high voltage side. That is, you have to calculate its primary side turns, its secondary side turns. Number two, current on the primary side and the current on the secondary side. And number three, area of the primary side and the area of the secondary side. Clear? So hardly we have to calculate the three main things in case of a winding design. So we will proceed towards. Okay. Now, number one point will be you have number of turns. Clear? So the very first step is the number of turns in the low voltage side. Now you can remember whenever you get a design in the terms of winding of a transformer, we never calculate the turns on the primary side, we never calculate turns on the secondary side. जब भी हम लोग अपने ट्रांसफॉर्मर का डिजाइन करते हैं तो ट्रांसफॉर्मर के डिजाइन में कभी भी प्राइमरी साइड के टर्न्स या सेकेंडरी साइड के टर्न्स नहीं निकाले जाते. टर्न्स निकाले जाते हैं लो वोल्टेज साइड के और हाई वोल्टेज साइड के. नो यू हैव टू सी कि आपकी लो वोल्टेज कहाँ है. अगर तो लो वोल्टेज प्राइमरी साइड पे होगी और हाई वोल्टेज सेकेंडरी साइड पे होगी तो ट्रांसफॉर्मर स्टेप अप होगा. और अगर आपके ट्रांसफॉर्मर की लो वोल्टेज सेकेंडरी साइड पे होगी और हाई वोल्टेज प्राइमरी साइड पे होगी तो ट्रांसफॉर्मर आपका नो डाउन स्टेप डाउन होगा. सो फर्स्ट ऑफ ऑल यू हैव टू कैलकुलेट इट्स low voltage turns rather than the primary turns, rather than the secondary turns. We have to calculate its low voltage side turn. Now in particular numerical, what is the voltage we have given? We have given 11,000 by 400 volt. That means you people tell me low voltage कौन सी side है, primary side पे या secondary side पे?
Secondary side पे, sir.
Secondary
sir.
side. Secondary side पे. That means your secondary side will be 400 volt and your primary side will be 11,000 volt. सो दैट मींस आपके सबसे पहले टर्न्स कहां निकलेंगे, लो वोल्टेज के, और वो लो वोल्टेज के टर्न्स कौन से होंगे, सेकेंडरी साइड टर्न्स होंगे या प्राइमरी साइड टर्न्स होंगे?
सर लो वोल्टेज तो सेकेंडरी में होगी ना?
सेकेंडरी में होगी, ठीक है। सो मेरा यहाँ पर मेन मोटिव ये है समझाने का कि जब भी हम टर्न्स निकालेंगे ना बच्चे, तो टर्न्स में वी नेवर यूज द टर्म प्राइमरी साइड सेकेंडरी साइड, वी कैन यूज लो वोल्टेज एंड हाई वोल्टेज. So for calculating of the turns on the low voltage, you can use the formula that is voltage on low voltage upon ET. Clear? अभी ये मेरी एक थियरी है, इसके बाद हम इस न्यूमेरिकल को कंटिन्यू करेंगे जहां आप लोग न्यूमेरिकल सॉल्व करेंगे इसी न्यूमेरिकल को. And after that you can calculate the value of high voltage and you can use the formula here. You can never use the formula that is voltage on high voltage upon ET. No, you can use the formula VHV upon VLV is equal to THV upon TLV, and this formula comes from your turns ratio. So that means first of all when you have to calculate its winding design, so in case of a winding design, firstly you have to calculate the voltage on the low voltage side, and if you divide this voltage on the low voltage side by ET, you can get a number of turns on the low voltage side. And after that you can use the formula of turns ratio, that is VHV upon VLV is equal to THV upon TLV. So by this method you can got a value of low voltage side turns as well as high voltage side turn. So it is clear to all of you?
यस सर.
नाउ अनदर वन थिंग, एक चीज का और ध्यान रखिएगा, मुझे एक चीज बताइए, क्या टर्न्स कभी फ्रैक्शन में हो सकते हैं? लाइक जब आप लोग लो वोल्टेज को ईटी से डिवाइड करोगे, लेट इट बी योर वैल्यू विल बिकम एज 10.3. सो कैन यू यूज दिस 10.3 एज द टर्न्स?
नो सर.
So what the values you have to be taken out?
सर 10 और 11.
Now the question is, make it a clear. एक चीज का ध्यान रखिएगा डिजाइन में, you should never go to lower side. You should always go to the higher side. Always. That means if you got a value that is 10.1, you should take the turns as 11. And if you take if you get a value 10.9, in that case you should also take a value as 11. Clear? You should never go to your lower side. Always go to higher side. Clear बच्चे?
सर क्वेश्चन है एक.
या बोलिए.
सर जैसे पहले वाले आपने फॉर्मूले में लिखा है ना कि नंबर ऑफ टर्न्स ऑन लो वोल्टेज साइड इक्वल टू वोल्टेज ऑन लो अपॉन ईटी.
या
सर हाई वाले को भी हाई वोल्टेज साइड वाले को ये वाला फॉर्मूला लग सकता है क्या?
नहीं. मैंने यही चीज आपसे एक्सप्लेन की है कि जब भी
वोल्टेज ऑन हाई वोल्टेज साइड.
नहीं बच्चे, नहीं. मैंने तभी आपसे बात की है कि जब भी हम ट्रांसफार्मर का डिजाइन करते हैं, हमेशा पहले हम लो वोल्टेज की वैल्यू निकालते हैं बाय यूजिंग अपर फॉर्मूला, और जब हमारी वैल्यू अपर फॉर्मूला से निकल जाती है उसके बाद हम लोग क्या करते हैं, टर्न्स रेशियो का फॉर्मूला लगाते हैं. और टर्न्स रेशियो का जो फॉर्मूला है वो यही कहता है, अगर आपको याद होगा फोर्थ सेमेस्टर थर्ड सेमेस्टर, दैट E1 upon E2 is equal to T1 upon T2, that is VP upon VS is equal to VP upon TS. तो हम इसी फॉर्मूला से हाई वोल्टेज के टर्न्स निकालते हैं. सो द क्वेश्चन आपने जो याद रखना है वो ये रखना है कि कभी भी टर्न्स हमारे फ्रैक्शन में नहीं होने चाहिए. That turns should always be in a real number and it will be on a higher side. If you got a value that is 9.2, make it a 10. If you get a value 9.1, make it a 10. If you get a value 9.9, make it a 10. Clear?
Yes sir.
Shall I proceed?
Yes, sir.
Yes
Okay.
sir.
This is the first step that I will tell you. In winding details, you have to calculate the three main things. This is the one thing you have to calculate the turns. Now, after getting the turns, we have to calculate area of the low voltage and area of the high voltage. Now see, area of the low voltage winding is given by simply ILV upon current density, and area of the high voltage side is given by IHV upon current density. Clear? Clear Z? And the current density, the value will be given to you. In this case, the value will be 1.4, isn't it? Isn't it?
Yes, sir.
Okay.
Yes, sir.
Okay, now see, the third step, you have to calculate the value of ILV. The formula is like this thing, that is ILV is equal to Q upon VLV and IHV is equals to Q upon VHV. Clear? Now यहाँ पर एक चीज का ध्यान रखिएगा. When you calculate ILV, the formula will be Q upon VLV. Now the question is, Q is in kVA and V is in volt. Again, I can repeat, Q is in kVA, that is kilovolt, and voltage is in volt. So that means you have to convert Q into voltage. So here you have to multiply into 10 raised to power 3. For example, in this particular case, your Q will be 5 kVA. So here I अगर आपको निकालना है तो I की वैल्यू क्या होगी? 5 into 10 raised to power 3 upon VLV. VLV means 400. Clear बच्चे? And similarly, जब आपको IHV निकालना है तो IHV की वैल्यू क्या होगी? 5 into 10 raised to power 3 upon 11,000. Clear बेटा? Clear?
Yes, sir.
Okay.
सर
Now
एक
when you,
क्वेश्चन है
yeah, please.
सर, जब हम ट्रांसफार्मर डिजाइन करते हैं ना, वहाँ पे लो वोल्टेज और हाई वोल्टेज वाली साइड हम कॉपर की वाइंडिंग्स यूज करते हैं
जी
मेनली।
जी जी।
तो सर जो वाइंडिंग होती है ना सर, उसमें डिफरेंट गेजेस होते हैं, उसकी कैलकुलेशन कैसे होती है?
वही तो कर रहे हैं, वही तो कर रहे हैं, मैं बता रहा हूँ ना आपको, वही तो कर रहे हैं, उसी की तो कर
सर
डिफरेंट
ये
गेजेस 24 25।
अभी जस्ट अ मिनट ना, वही तो मैं करके बता रहा हूँ ना आपको। अभी हमने ये किया है, मैं पहले विनायक के क्वेश्चन का आंसर दे दूं। अभी विनायक हम ये कर रहे हैं कि लो वोल्टेज पे टर्न्स कितने होंगे और हाई वोल्टेज पे टर्न्स कितने होंगे, वो हमने निकाल लिया। दूसरा जो तुम्हारा क्वेश्चन है कि जो कॉपर वायर यूज कर रहे हैं उसका गेज क्या होगा, गेज के लिए तुम एरिया निकाल रहे हैं, क्योंकि गेज डिपेंड करेगा एरिया के ऊपर, और एरिया ऑफ द लो वोल्टेज का फॉर्मूला मैंने दिया ऊपर कि करंट अपॉन करंट डेंसिटी। तो करंट वैल्यू कैसे निकाली, वो इस फॉर्मूला से आपने निकाली, दैट इज द आई विल टेल यू ना।
ये सर, ये सर।
हाँ जी, सार्थक बोलो।
सर ये रिपीट करना है फिर से, ILV और Q अपॉन VLV।
आईएलवी निकालने का फॉर्मूला है दैट इज Q अपॉन VLV। Q अपॉन VLV में मतलब जो Q है आपका, वो जो Q है दैट Q इज बेसिकली इन KVA, और वोल्टेज जो है दैट इज इन, यू कैन से दैट इन simple voltage. So we have to convert this Q kVA into 10 raised to power 3. That means अगर आपको यहाँ पर Q 5 kVA दिया है तो 5 into 10 raised to power 3 अपॉन आपको 400 वोल्ट करना है। क्लियर?
सर मतलब केवीए को वोल्ट एम्पेयर में चेंज करना है।
या एब्सोल्युटली एब्सोल्युटली एब्सोल्युटली। जब आप नीचे न्यूमेरिकल देखोगे आपको क्लियर हो जाएगा कि मैंने कन्वर्ट किया है। ठीक है?
ठीक है सर।
अच्छा, एक और चीज, नाउ अब आपके पास यहाँ पर ILV निकल गया, आपके पास यहाँ IHV निकल गया, करंट लो वोल्टेज की निकल गई, करंट हाई वोल्टेज की निकल गई। सो एरिया क्या है, दैट इज ILV अपॉन रो, एंड हियर एरिया क्या है, IHV अपॉन रो। नाउ अगेन यहाँ पर ध्यान रखना, ये जो मैंने रो की वैल्यू लगाई है यहाँ पर उसको मैं मीटर स्क्वायर में कन्वर्ट नहीं करूंगा। क्लियर? सो मेक इट अ क्लियर कि करंट डेंसिटी की वैल्यू जब मैं आउटपुट इक्वेशन में डालता हूं तो 10 रेज़ टू पावर 6 करता हूं, लेकिन यहां पर मैं नहीं करूंगा बिकॉज एरिया हमेशा mm में होता है। जब आप बाजार में वायर खरीदने जाते हो, कोई भी वायर लेने जाते हो, तो आप सबसे पहले पूछते हो 1 mm की वायर दो, 2 mm की वायर दो, 5 mm की वायर दो। दैट मींस एरिया विल ऑलवेज बी इन mm. सो हियर आई कैन नॉट यूज दिस वैल्यू in meter square, I can take it this value in mm. Clear?
Yes sir.
Okay, now this is one of the most important thing also that I have read down in red pen, that when the cross sectional area, जब आप एरिया निकालेंगे लो वोल्टेज का, एरिया निकालेंगे हाई वोल्टेज का, when the cross sectional area of the conductor is greater than 5 mm square, जब आपका एरिया LV या एरिया HV का 5 mm से ऊपर आता है, we can use rectangular conductor, and अगर एरिया कम आता है 5 mm से तो we can use circular conductor. So for calculating of the circular conductor, जो विनायक आप पूछ रहे थे गेज का, तो गेज का ये फॉर्मूला है दैट इज D is equals to अंडर रूट ऑफ एरिया ऑफ द वाइंडिंग इनटू 4 अपॉन पाई। सो यहां से आपके पास एक आइडिया मिल जाएगा कि आप कितनी गेज वायर को यूज करोगे प्राइमरी साइड पे, सेकेंडरी साइड पे। सो एक चीज का ध्यान रखना, सेम वायर कभी यूज नहीं की जाती प्राइमरी साइड पे, सेम वायर कभी यूज नहीं की जाती सेकेंडरी साइड पे, डिफरेंट वायर्स यूज की जाती हैं। और ये वायर जो प्राइमरी साइड या सेकेंडरी साइड पे यूज की जाती हैं, ये डिपेंड करती हैं कि आपकी करंट की वैल्यू क्या है। So depending upon the current value, we can use the value of wire in a primary as well as in a secondary. Clear बच्चे?
सर रेक्टेंगुलर कंडक्टर क्या होता है?
रेक्टेंगुलर कंडक्टर मतलब जिसका क्रॉस सेक्शनल एरिया जो है रेक्टेंगुलर होगा।
ठीक है सर।
ठीक है जी, क्लियर है? क्लियर?
Yes, sir.
So you can see in this particular numerical the number of turns on the low voltage side. First of all, we have to calculate the number of turns on the low voltage side. So here, what is your ET? We have voltage upon ET. लो वोल्टेज थी मेरी 400 और डिवाइडेड बाय मैंने ET से किया, I got a value 1.62. when you divide this value, you can get 246.45. I can tell you that this value should always be take on an even higher side, so the value will be 247. So here the low voltage turns will be equal to 247. Same formula I can use, turns ratio, that is VHV upon VLV is equal to THV upon TLV. So we have THV मेरे पास नहीं है, TLV मेरे पास है, that is 247. VHV will be 11,000 and VLV will be 400. So 11,000 by 400 multiplied by 247, you can get a value that is 6793. So you are getting a number of turns on the high voltage side will be 6793. It is clear? So after that you can see area of the low voltage side. Area of the low voltage side will be ILV upon current density, and for calculation of ILV, I can tell you that 5 kV upon the voltage. So 5 into 10 raised to power 3 upon 400, current will be 12.5, and IHV is equal to same 5 into 10 raised to power 3 upon 11,000. Value will be 0.45. So you got a value ILV, you got a value IHV. Now simply I can divide ILV by current density and IHV by current density. You can get an area of the winding on low voltage, area of the winding on the high voltage. Now you can see area of the low voltage. That means 12.5 upon 1.4. Value will be 8.928. And second case 0.45 into 1.4. Now you can see low voltage winding is having area greater than 5 mm square. We can use rectangular conductor. Area of the high voltage side is less than 5 mm square. We can use a circular conductor. And when you use the circular conductor, you can use the value that is D is equal to root of area of the winding into 4 upon pi. You can get a value D is equal to 0.6428. So this combines the main dimension as well as the winding of the design. I think you all got this an idea.
रेक्टेंगुलर वाइंडिंग होती है ना सर?
जी जी जी
सर जैसे रेक्टेंगुलर वाइंडिंग होती है ना सर, उसमें भी गेज होते हैं क्या?
हाँ हाँ, नहीं नहीं, उसमें गेज नहीं होते हैं, उसमें आपका लेंथ इनटू ब्रेड्थ आ जाती है। गेज का मतलब क्या होता है, सर्कुलर जब होगा, सर्कुलर में जो गेज होता है वो सबसे स्मॉल, यू कैन से दैट, उसका क्रॉस सेक्शनल एरिया होता है। आई विल डिस्कस विद यू कि जब हमारा रेक्टेंगुलर कंडक्टर होगा तो उसमें गेज नहीं होता, लेकिन उसमें लेंथ इनटू ब्रेड्थ होती है। हम लोग देखेंगे कि वो
कैसे पता चलेगा,
वो मैं बताऊंगा, फॉर्मूला बताऊंगा। जैसे मैंने आज आपको इसका फॉर्मूला बताया ना, वो भी फॉर्मूला बताऊंगा आपको, नो इशू एट ऑल।
ठीक है
सर।
या सार्थक
सर जब हमने सर्कुलर राउंड कंडक्टर निकाला तो सर हमारा जो रेक्टेंगल है सर वो 8 पॉइंट आया कुछ।
हाँ जी।
और सर्कुलर आया 5 से नीचे। हमने सर सर्कुलर देखना होता है कि सर्कुलर की वैल्यू छोटी है।
बेसिकली यहाँ पर क्या है कि हमने ये देखा कि जब हमने वाइंडिंग करनी है लो वोल्टेज पे, तो लो वोल्टेज पे हम लोगों को रेक्टेंगुलर कंडक्टर यूज करना है, और जब वाइंडिंग करनी है हाई वोल्टेज पे तो हम लोगों को सर्कुलर कंडक्टर यूज करना है। अब जब सर्कुलर कंडक्टर यूज करना है तो उसका हमें गेज निकालना होता है, जो विनायक कह रहा है, गेज का मतलब डायमीटर निकालना है। तो डायमीटर निकालने के लिए मैंने ये वैल्यू दे दी है। तो दैट मींस कभी भी जब आपका एरिया 5 mm से नीचे आएगा तो आपको अगले स्टेप में प्रोसीड करके उसकी डी की वैल्यू निकालनी होती है, और अगर 5 mm से ऊपर आएगा तो हमें वैल्यू नहीं निकालनी होती। क्लियर?
ओके सर, ओके।
या नाउ इट इज क्लियर। सो विद दिस
अगर 5 mm से कम आए तो हमने
या बिल्कुल। So with this you have calculate it's the main dimension. After that you have calculate the winding length. So with this numerical you have to clear all the concepts behind that, how the main dimension of this transformer can be calculated and how the winding details of this transformer can be calculated. Clear? I can put this study material on your WhatsApp group and also share this video. You can watch this video carefully and after try to solve this numerical. And again, if you find any problem, you can tell me. I will provide you another material. And in my next lecture, just a minute. In my next lecture, we will practice these numericals. Okay. Now, tell me, Vinayak.
सर अगर ना 5 मिलीमीटर स्क्वायर से ज्यादा एरिया आता है तो ये कंपलसरी है सर कि हमें रेक्टेंगुलर कंडक्टर
एब्सोल्युटली रीजन बीइंग, अगर हम लोग 5 mm से ऊपर एरिया आता है और अगर हम वहां पर सर्कुलर कंडक्टर यूज करेंगे तो वो सर्कुलर कंडक्टर जो है वो आपकी वाइंडिंग को नहीं कर पाएंगे। रीजन बीइंग, ये जो कंडक्टर हम लेते हैं, ये लेते हैं डिपेंडिंग अपॉन द करंट, और अगर करंट की वैल्यू ज्यादा होगी दैट मींस उसमें लॉसेस ज्यादा होंगे, तो देयर विल बी चांसेस कि उसमें हीट डिसिपेट ज्यादा हो तो वो वाइंडिंग को डैमेज कर सकती है। So it is a rule, it is a mandatory rule, it is a design rule that whenever you have the area greater than 5 mm square, you can use a rectangular conductor, and whenever you can get a value lower than 5 mm square, you can use a circular conductor. Always.
सर जब हमको रेक्टेंगुलर निकालना होता है सर, तो हम उसकी वैल्यू निकालते हैं, हम सर्कुलर निकालते तो हम सर्कुलर में हम हाई वोल्टेज सर्कुलर करंट से हम उसकी वैल्यू निकालते हैं।
हाँ
यही है ना सर?
मैंने यही बताया ना कि जब आपको देख रहे हैं कि एरिया क्या है, अगर एरिया 5 mm से ऊपर है देन रेक्टेंगुलर कंडक्टर, और अगर एरिया 5 mm से कम है सर्कुलर कंडक्टर। और अगर सर्कुलर कंडक्टर है, चाहे वो लो वोल्टेज पे है चाहे वो हाई वोल्टेज पे है, आफ्टर दैट यू हैव टू कैलकुलेट इट्स डायमीटर, यू हैव टू कैलकुलेट इट्स डायमीटर। क्लियर?
यस सर।
ठीक है जी। सो
में आएगा ना?
या ऑलवेज एरिया हमेशा जो होता है वो mm